small limit to how much differential voltage I can put across the circuit without it hitting the power supply rail. And in this case, for this lousy op amp, it is around 0.2 volts, which is huge. That's not a very good op amp. We keep increasing VID. As we increase VID, this voltage here is going to go up. This current ID is going to go up. This current over here, ID, is going to go down. This gate voltage is the negative of VID, so this one's going to go down. VG2 is going to go down. As ID increases, VD is going to go down on this side, and VD is going to go up over here, and VS is going to stay roughly the same. So the VS is going to stay roughly the same. The VGS of this transistor, since ID is going to go up, is going to go up. VGS over here is going to increase. This VGS is going to go down. Eventually, one of the transistors is going to turn off. It's going to go out of saturation, and we're going to hit the power supply rail, is the final limit. Now let's look at some pictures here of gain curves. This is kind of instructional too. I have an absolute limit here of I can't go below minus 1.4. I can't go above plus 1.4. The gain is nice and linear and looks like a straight line during most of this region. And it looks like a straight line for both of those transistors right here. And this is as I increase VID. It gets to the point when before I hit that absolute maximum limit, it stops looking like a straight line in this region. If you get too close to the absolute maximum limits on these transistors, they stop behaving well. You'll start to see gain distortion. You'll start to see the gain rolling off. You'll have really low gain. You don't want to operate a circuit close to its power supply limits. Now this gets to be a problem. Let's say you've got a 50 millivolt signal coming in, and you're trying to run this circuit off of a 5-volt power supply reference to ground. Your 50 millivolts is really close to ground. You're going to be in one of these gain regions where you're not very linear. You're not going to have a lot of accuracy there. And the only way to fix that is either to add a DC offset to the 50 millivolts, which is going to be sloppy, or put a negative power supply in. Okay. Things I yell about in the lab. But the Arduino only has it doesn't have a negative power supply. We got to make a negative power supply. It won't work. You've got a 50 millivolt signal here. You're trying to get this down to like a highly accurate level. And you want to look at this on the microvolt level too. You care about what's going on. It doesn't work anymore. The gain region is that region in the middle where you have slopey stuff, and you want it to be linear. You want it to be a straight line. What happens if I increase the V over voltage? If I increase, that doesn't look right. If I increase the V over voltage, the slope changes. So I can change the gain of the transistor by increasing the V over voltage. The advantage is with the lower V over voltages, I have a steeper slope, but I have a smaller region where it will work. I can only go plus and minus 200 millivolts, or sorry, 200 millivolts, but I have a higher gain. If I go to a higher V over voltage, the gain is lower, but now my linear region is out like around 500 millivolts. It's always a trade-off. When you have a high gain, you get a very small region of operation. If I have a lower gain, I get a larger region of operation. That's all I wanted to say about that. Small signal operation of the MOS differential pair.
Sorry,
Yeah, thank you. Go ahead.
So how does it apply to our transistor?
The W over L, oh, like this. To do this with my finger. Okay, I'm not going to write my fingers. Home, let's do this. Draw. Okay, now I can do it. You have this equation right here. ID equals Kn prime W over L VOV squared. If I put in a bigger W over L transistor, I'm going to have a higher ID. I'm going to have a lower V over voltage. Yeah, so it all relates back to that equation. If you're confused at any time during the exam, you don't know anything else, write down that equation, write down Ohm's law, and write down KCL, and you might, and write down everything you know on the schematic, and that will get you far. What? That's exactly what we're doing on the homework. Yeah. We want to look at the small signal operation. Okay, so we want to figure out what is the gain of this. What did I tell you when we started this? If you have to guess, if you have to guess the gain of anything, GMRO always works. I at least won't think you're silly. Okay, we want to draw the small signal circuit. So the small signal circuit, I get rid of, this becomes a short. My current source becomes an open, so I can just cut that wire right here. My DC sources become grounds. And my other signal sources stay in. Yes, I do. I've got, so that is the AC circuit. And on the next slide, I'm going to redraw that more neatly. There is the AC circuit right there. Okay. My AC circuit, I've got the differential signal on there. Since it's perfectly symmetrical, I could just split this circuit in two and have what we call the differential half circuit. What is the gain formula for that? What kind of amplifier do I have on that differential half circuit with a virtual ground? Because the source voltage can't change. And it's the same on both of them. So we just call it an AC ground. What kind of amplifier do I have in the half circuit? Inputs on the gate, the outputs on the drain.
Common drain.
Common source, good, thank you. It's a common source amplifier. What is the gain of a common source amplifier? It is GMRO. And there's a negative sign in there. Through the magic of algebra, we're going to get rid of the negative sign. We'll do that in the next slide. But the gain of this is going to be, this half circuit is going to be GMRO over 2 because I've got the 2's in there or something like that. Okay, here's how we do the algebra. We calculate the gain of one half circuit. I get, oh, that's just scary when that happens. Home, draw, and great. Undo this. Just hit draw with touch. Hold on. I'm trying to find the little magic thing that makes this work. Home, draw. Don't draw with touch. Draw with touch. I can only use my fingers. right here, I get the gain of one of the sides on it. It has a negative sign because I have a negative VID over 2 on it. Or it has a negative sign because I don't have a negative VID on 2 of it. The gain of that common source amplifier is the negative of a negative. And so this one becomes positive. Just ignore everything I just said right there. One of them has a negative input, the other one doesn't. The gain of the common source amplifier is negative, so one of these is going to come out to be negative and one of them's not. When I add them together to find the differential gain, it's VO2 minus VO1, and VO2 minus VO1 as minus a negative, so the two halves add together algebraically and make it positive GM big RO. If it does, yes, exactly. If the sign comes out wrong, you just flip the wires around. 90% of my errors when I was designing circuits could be fixed by just putting an inverter in. This is why simulators are so great. Okay, I'm sorry. I have a sign error issue. My son did too, and it drove his algebra teacher in 7th grade crazy. And so she would just mark everything wrong. It'd all be sign errors. And he failed algebra all because of a stupid sign error, which is pointless, right? Sign errors are not that important. This is how I started homeschooling him. So I put him through the most rigorous algebra class you have ever seen. It took us 2 years to get through it. But by the time he got through it, algebra 2 was a cinch. Trig, pre-calc was easy because he had all that. But when we occasionally made sign errors. So if we want to calculate the gain for this, it's basically GMRO. What's going to dominate this? Oh, thank goodness. RO, it's going to, RO, if we look at our output resistance, is going to be RO2 in parallel with RD. When I put 200 K ohms in parallel with 8K, I get a number a little bit less than 8K. In fact, drum roll please, that comes out to be, oh, and I didn't do the calculation, 200 times 8K over 208K. So the VO, the voltage gain, oh, yeah, this is just wonderful. AD equals GMRO. So it is GM is 1,000 micro. My RO is 200K in parallel with 8K, which is going to be a little less than 8K, and I didn't actually calculate that. And this is going to come out to be 7.69. Did I really do that? Yes, I did. 7.69. I'm amazed the way I used to solve things. And that's volts per volt. And if I want to find that in dB, I just take 20 times the log of 7.69, because this is a voltage gain. And that comes out to be 17.7 dB. So the punchline, you can go through, you can convince yourself with the derivations in the book if you need to, but the gain of this differential amplifier is going to be positive GM big RO. Are we almost done? No, I mean, I'm I'm looking for my slide, my stopping point. What is the formula for the differential gain here? Okay, so that was with a resistor load. This is the same thing here. I still have the same GM, and it's not writing anymore. I still have the same GM, and the units are wrong. That should be microamps per volt. I still have the same RO in. I still have the same GM. The only thing I'm changing here is instead of having that 8K ohm resistor, I'm now looking into the drain of a PMOS transistor, which has 100K ohms. So all I've done is increase the RO of my current source. What happens to my gain? My gain is still GM, I'm using my finger, I'm sorry. RO. So this is going to be and it won't let me write it on now. Oh, now it will. Let me do this. Not use my finger. Equals 1,000, and the units here are wrong. It's microamps per volt. I don't know where that came from. 1,000 is the GM of my N transistor. My gain transistor, let me move you guys over. Everybody lean to the left. My gain transistor is still this transistor. These are current sources. They're not going to be the GM. So which GM am I going to use? I'm going to use GM1 or GM2, and they better be matched. Those are the gain transistors. My RO now is 200K in parallel with 100K, which should be a little less than 100K. And when I do that calculation, that comes out to be, well, that's 66.7K is what it is. And when I do the overall calculation, it is 66.7 volts per volt. How much have I increased the gain by? It was 7.69. It's a factor of 10. So having that high output resistance transistor there really helps. I could have improved the other circuit by putting a 100K ohm resistor there instead of 8K, but then I would have limited the amount of current I had. And in dB, that comes out to be a whopping 36.5 dB. So a much improved performance by putting these in an integrated circuit. And about sometime in the early 60s, Burr Brown came up with the idea of putting the, I want to say around 65, 66, came up with the idea of putting these op amps in an integrated circuit and putting a high gain common source output stage on it, putting a low gain buffering common drain output on it, integrating all the circuits in and calling it an op amp. And they invented the 741 op amp. There's a little company called Burr Brown down in Tucson. And that is now a small division of TI. As the world goes, everything's a small division of some other megalithic company now. You get a good idea, you're a small company and you get a good idea and you start selling things, and then you realize the volume selling isn't as much fun as the inventing things. And so you sell it out and you make a lot of money and you stay along to manage it for a few years. And then the big companies get new ideas by going out and buying these smaller companies. It's the way the world works. How can I make this better? I could cascode the diff amp. Okay, what have I done here? What horrible thing have I done here? My output is right there. It's labeled V out differential. My input is right here. The gain of a cascode stage is the same as the gain of a common source stage, and it is, I will just tell you right now, the gain is GMRO. Which GM? It will be Q1 and Q2. These are the gain transistors. Those are the kind of the buffering transistors. So GM1 or GM2. I just moved you guys over again. The advantage to this, if I want to find the output resistance, it's going to be R down in parallel with R up. We get that multiplier in there. R down is going to be, go back to that handy dandy little chart, is going to be the RO of 4, and it has a transistor in its source, so it's 1 plus GM4 RO2. That is a much bigger number. R up is RO6. I can barely read that. RO6 times 1 plus GM6 RO5. What I've done with that cascode, just adding a couple more transistors in there, I've increased the gain, which decreases the limits, the voltage limits I can have on the input. And it also increases the output resistance, which means I need to buffer it. But I can get a much higher gain op amp just by cascoding it. I could triple cascode it and put a third transistor in there and make a ridiculously high gain op amp that would have a very narrow differential input range. I think I'm just about done. Yeah.
Isn't supposed to be GM6 times RO5?
Yes, that's a 5. I put 4 in there twice. That is, and I can't write anymore. This is a RO4 there. Should be a 5. Well,
in the source of the Q6 is Q8.
Oh yeah, sorry, Q8. Never mind. So this should be. Well, we'll just fix this even more. That is Q8. I can't read those numbers on there, so I just took your word for it. So it's Q6, and on the source you see Q8. Either way, yeah, those are going to be pretty big numbers. That is it, and I'm out of time. Thank goodness. This has been a hard day. Okay. All right, let's see, who do I have missing? Remember to sign up for a remote exam if that's what you want. It's easy to send me an email. I just want to make sure you're available the same time I'm available. And I will negotiate with you if I have to. Gabriel, Victor, and Chris Weber. Okay, and everybody else is here. Oh, you can, what? You saw Gabriel with a little slash after his name? That's Gabriel Martin. This guy right here, that's Gabriel Martin. It was Gabriel Baldwin. Oh my God, I have absent. Okay. I know that. The Zoom world's entirely too normal. I'm sorry. Okay. Unfortunately, I can. That's the disturbing thing about life in the Zoom world. Okay, I'm going to